My name is CARLO JAEGER. I will say a few words about me in a moment, but first I want to thank you for being here, especially those who with amazing stamina are overcoming jet lag, and the people from INT, of course, for making this possible. It's a mixed blessing for me, because giving a talk, and the first talk, to an audience composed of world-class specialists is, of course, a bit challenging sometimes. But it's nearly mission impossible when the specialists come from very different fields, as is the case in this room. I should also say that's exactly why I do what I'm doing, because I think this sometimes leads to real creative outbursts. Let's not forget that computer science was born from the meeting between electrical engineers and mathematicians. Molecular biology from a meeting between physicists inspired by Schrödinger and Delbrück and old-fashioned biologists. So it is worth to make the effort to bring people from two very different communities together and try to work on it. And keep in mind that it usually takes very small groups of people to do these things. The large structures, they emerge much later. Now, how far we will get there remains to be seen. But I want, with my talk, to share with you why, in my opinion, it is not only intellectually interesting and perhaps rewarding in financial terms, but it's actually a serious responsibility. It's actually important in a deeper sense. I want to focus on systemic risks. And what I want to say, for those in jet lag, if you have that sentence, you're done and, survive. The governance of global systemic risks will require global systems analysis powered by high-performance computing. About global systemic risks, I'll say a bit more. I'm thinking of things like climate change, large-scale geological disasters, vastly underestimated, financial crisis, and more. Now, synthetic populations, the topic of this conference, have not started there, but they are relevant to this. I will not talk about pandemics and the whole kind of work that has emerged there. There are people in the room who are world-class leaders in this field. Me, I'm not, so I'm not going to go into that. But I want us to be aware of it, that the tool of synthetic populations has already been used extremely successfully, and I would say in a really useful way, in this field, and there's some other fields. And there are people in the room who can share this with us, and will, to some extent. But you see, the question, why do we have these global risks, is not at all easy to answer. And therefore, the question of what to do about them is not at all clear. And that's what we better should look into. I want to start by giving you a few examples, one more extensive, the other ones I'll be very brief about. This is a brand new simulation about the coasts of the world and the sea level rise in this century. The colors are unfortunate because we intuitively think red is dangerous and green is harmless and nice. Well, it's the other way around. Green are the coastlines that actually need to be protected for various reasons in this century. Red are the ones where you can say, well, let's see a little bit what happens and not take a lot of action. Already, to do these computations, and this goes down to kilometers, is based on big data, of course, but also reasonably computationally intensive, not yet in the dimension of HPC we're talking about here. But if you now zoom in, then you see in Europe, we are in a good spot, We have here Scandinavia, Denmark, Germany, the whole Benelux without Luxembourg, northern France, the UK, and then on the Mediterranean, and I included on purpose North Africa, because, for instance, here, Cairo, Alexandria, etc., things will happen that most likely will affect Europe. So zooming in into these things is important, and I want to zoom in one more. This is just a scheme. You don't need to read the details. I'll share the idea with you. This is about London. In London, there's a lot of money, so they think carefully about how to protect the money. And this is 0 meter, 1 meter sea level rise, 2 meters, 3 meters, 4 meters. these are different actions that you can take. The point is, it is stupid today to immediately prepare for 3-meter sea level rise. We don't know whether it will happen, but we do know that better technologies will be available in a few decades. On the other hand, doing nothing is also stupid. So you need a sequential, iterative management strategy for these things. And what I want to share with you is simply the fact that we have the global coastline, whose length is not very well defined because of fractal geometry, but let's say it's really long. But then you have to zoom in. You have to look at Europe, you have to look at a place like London, you have to look at even smaller places. Prepare for sea level rise in this century is a task that will require the analysis of a global system with high performance computing capabilities and big data analytics capabilities. It is a practically important problem. It is also technically sweet. There are a lot of really difficult and interesting questions in there. For the moment, I just want to share this as an example of the systemic risks with which we are faced in this century and where people like the ones in this room have something to contribute. Just because it's fair to quote, the simulation I showed is due to Linke and Hinkle. It's just submitted on Nature Climate Change. The iterative coastal management idea is a paper by Hinkle and others, also on Nature Climate Change, already published. And because I'm in literature, and I think the PowerPoints will be available, about the idea of systemic risks, we just submitted a paper, Ortwin Wren, Klaus Lucas, and myself. And I want just you to have a glimpse of what this is about. Modern societies are very, very good, amazingly good in dealing with a certain class of risks, even if many people don't realize it. But the way we are dealing with many, not all, many illnesses, with car accidents, with fire, with floods, in rich societies, in advanced societies, is amazing, unprecedented in history. Just to give you an example, there have been 2 earthquakes of similar strength in areas with similar population density, one in California, one in Haiti. In Haiti, more than 60,000 people died. In California, less than 100. That's the degree of progress that we have made. So we are really good at dealing with certain risks. But there are other risks where we frankly are at a loss. We don't know what to do. These are the systemic risks. And one of the important aspects of systemic risk is that they are global, which is why this global system things comes in there. I just want to give you a few more examples, but I will be brief on these. Around the year 1700, in Japan, where they had records of tsunamis, they made a record of a huge tsunami, which to them was mysterious. Why? There was no earthquake associated. Normally, in the records of Japanese tsunamis, which goes back more than 1,000 years, they have an earthquake and the related tsunami. This one was just a tsunami. It was also coming from the open Pacific. Indian tribes in Oregon and around Vancouver have stories that anthropologists treated as mythological material about a huge flood with volcanoes, with earthquakes, with terrible things happening, roughly around the same time. It turns out that there is a fault line off the Pacific coast of North America. It goes all the way from California to Seattle. And this fault plate created twin tsunamis. One went east and one went west. It was large enough to seriously hit Japan. It was pretty devastating in North America. The people who study these things actually have no doubt that this will happen again. It will most likely kill something like 100,000 people in America. It will devastate an incredibly prosperous economic region in a way that you can recover from. But it's not going to take 2 weekends. It's going to take much longer. Now, some of the people in the room have done simulations about the effect of a nuclear blast. What happens then? And what you can do in face of these things. Of course, these are terrible things to think about, but we have to think about them. With regard to the Vancouver-Seattle area, As with regard to Japan, remember Tohoku Fukushima, preparation is miserable, is absolutely miserable. And we do not simply need simulations telling us that there will be a tsunami of strength X and things like that. We need simulations telling us what they will do to schools, what they will do to hospitals, what they will do to bridges. These things can be done. And I want to distinguish the analysis of a local flood from the analysis of an event of this category, which is going to have effects on the whole world economy and on world society as such. It's just a second example. Of course, there are similarities with the sea level rise example, but it's another story. And there's work to do for people like the ones in the room. Some people believe that migration is due primarily to climate change. I work on climate change. I think climate change is not the main factor, but it is an important factor. We need to be able to study migration movements in this century, both globally at a coarse resolution, and to be able to zoom in and go down to very, very specific paths, trajectories, changes in these patterns. This is a nice website where you can look at moving dots representing people. And it's another example of global systemic risks, because these migration flows risk to disrupt not only single society, but actually large-scale political arrangements. And there is a security aspect to this. Finally, in terms of risk, there is what I call the global financial spider web. All I want you to see is that there are lots of dots, and the dense area in the middle, this is Western Europe and the USA. This is basically New York, London, plus their periphery. My little country, Switzerland, sits in this spider web. It's not a major player, but still, you know, we are making some money out of it. And it is important to say that the Davos World Economic Forum is not by chance existing in Switzerland. This is connected with the role of Switzerland in this global web. There is such a thing as a global elite. It does meet once a year in Davos, and to be frank, it is at a loss in the face of systemic risks. It's not the case that the people who gather in Davos have a credible, well evidence-based and well thought through narrative and analysis of what's happening and what to do about it. They do make risk reports and things like that, but they do need the kind of research that out of meetings like this will hopefully emerge in the coming years. There will be a whole session about financial risks. I'm not going to go into that either. I just wanted to mention it. For all these things, we need synthetic populations. One reason you want synthetic populations in many cases is privacy. Here, this is also an issue, but more importantly, it's the fact that you simply don't get the one-to-one data. You have to infer population structure, patterns of relations, attributes, etc., as good as you can. But without global populations, not only of people, of institutions, organizations, cities, etc., you cannot analyze these things. And I want to look at the last issue, which is not only and not even mainly about the risk. It's global innovation dynamics. There are statistics about these things. The results are quite impressive. What they show is that, and it's based on patterns and things like this, it goes closely with population density multiplied by income per capita, and it goes very closely with density of population. You get innovation if a lot of people are packed in a small space and are reasonably affluent, which means you get innovation on the east coast of the US, on the west coast of the US, not in Europe in general, but on, sorry for the word, an axis that runs from London and Stockholm, it's a bit of a Y here, all the way up the Rhine Valley until central Italy. We don't see on this particular picture Southeast Asia. I can tell you, and I want to tell you, that the picture there is less clear than some people may think. Japan, of course, is a hub of innovation, but it's not as strong as the ones in the West. South Korea is amazingly strong. Of course, China is doing what they can to enter this game, but they are not yet in it. But it looks like rather soon China will be in it. And this then leads to all sorts of disruption of geographical and economic patterns between Tokyo, Seoul, Shanghai, Beijing, etc. This kind of dynamics I mentioned for two reasons. First, because it comes with a risk, namely the risk of inequality. But second, it's relevant to people who are not so interested in this kind of risks, but who are interested in business. So from a business point of view, to understand the dynamics on innovation on the planet is important. And I'm not talking only now about high-performance computing. I'm talking about T-shirts. I'm talking about food, everything. Innovation is key for economic dynamics. And this leads me to a little terminological quibble. I use the word synthetic population for a static snapshot. There is no canonical definition of these things. It's not so important. But conceptually it is important, and I will move to that, to distinguish between the static snapshot, which typically is an initial condition of a dynamical system, but that's not necessary, and the specification of the dynamics. And the specification of the dynamics typically is a Markov chain in a format which usually you can describe as an agent-based model. And together these two things, in the terminology that helps me to organize my mind, I call a synthetic information system, picking on the things that Chris has explained long ago at some of our meetings. Now all this, I think, makes a case for the need to expand on the successes of synthetic population research in the direction of studying global systems powered by high-performance computing. Now, this raises two intellectual challenges, and I like intellectual challenges, and I want to share them with you. The first is what I call the multiplex challenge. We deal with networks here, but we deal with networks and of networks, and we deal with interference with networks, and I'm impressed and honored by the fact that in this room are some of the world leaders in the science, not only of networks, but actually of interacting and multi-level networks. I'm not one of these people, but I like this work and try to use it. We are at the beginning. We already know a few things, but much more is to be discovered, especially when you apply it to global systems. Not going into this now, but I think that in the coming 2 days we'll have opportunity to look a bit at it. Now, the reason I emphasize this is to make a distinction, which in my opinion is usually blurred and sometimes ignored. It's the distinction between the importance of networks in what I call the real world. So, people, for instance, are married, they have children, they divorce, they have kin, they have friends. These are networks of people. Banks give credit to each other, own equity. These are networks of institutions. So these are networks out there in the real world. Global systems are always about the interaction of such networks with the network of nations. Today in the world there's about 200 nations. Some of them are actually not so stable that you are sure they will still be around in 20 years, but some of them are actually amazingly stable. China is around since several millennia, so I would bet that it will still be around in a few years, but we'll see. But the study of these networks in the real world is one task, and it's a task of global systems science. Now, if you want to make simulations about the dynamics of such things, you do need parallel computing, and parallel computing has networks of its own. There are networks of these cores, processors where computations run, storage, media in different places and stuff like that. These things, of course, in a good implementation will be related, but they are not the same. It's not useful to simply try to map one-to-one the network from the real world on the network you're dealing with on the machine. And how to efficiently relate these two things leads to my final point, and then I'm done. Namely, what's called the performance abyss that widens increasingly between theoretical math and the practical use of HPC systems. This is from a contribution by Ulrich Rüede to a workshop of the Department of Energy on mathematics for exascale. Now, it's not my field. I don't have anything useful to say about exascale, except that there are people who seem to know their trade, who say that with the kind of mathematics that we have considered sufficient to do supercomputing up to now, and which probably was not sufficient, it was just what we dealt with, we will not be able to harness the potential of exascales and even steps in that direction. And let me conclude with a slightly pessimistic note. This man, Ulrich Rüede, to me is a very good example of the problem of Europe. So the Americans run a workshop on math for exascale computing. They invite the best people all over the map. They make a nice little booklet. It's all on the internet. Among the people they invite is one German professor in Erlangen. Now, Erlangen in mathematics is quite a place, like Göttingen or so. Most of the papers are very technical about various intricacies of high-performance computing, especially when you move towards exascale. Some of the papers are more strategic, conceptual, in a long-term research perspective. And one of the few people who did this is this guy, Ulrich Rüede. Now, in America, there is still, remember the global innovation dynamics, there is still an innovation system that creates resonances between this kind of very theoretical work, technology development fostered at the level of government, and then businesses. Frankly, we don't have a lot of this in Europe. And it is strange, and it is something that better changes if we want Europe to still be around in a few decades. What we are doing is just one example. It's not the most important, but it is an important example. So let me simply conclude by saying that it seems to me that harnessing high-performance computing for dealing with global systems, both in view of risks, but of course I could also have given a talk about opportunities, I just chose this one. Doing this is useful, is important, is challenging. I would go as far as to say it comes with a pretty serious responsibility. And there are different difficulties in different parts of the world. Europe has its own problems, and I hinted at one of them. I think it's not politically incorrect in Luca to say that America also seems to have some difficulties to get its act together, to put it in a bit jokingly form. There is a lot of stake in dealing with global risks. There's a lot of stake in dealing with global systems. It will not be easy to provide the technical and scientific tools to deal with it, and it's our task. Thanks for being here and for sharing the effort.